Recently, I found this schematic on a website, which I will link in the description, and it is supposed to be a discrete-only curve tracer for bipolar transistors. This is the same circuit built on a breadboard, and after you connect an oscilloscope in XY mode, you obtain this. This is the collector current collector voltage characteristic of the transistor under test. You can see that there is some noise, but building it on a PCB would probably improve it, and that the x-axis is inverted. Not much we can do about it. There are plenty of videos showing this circuit, but I couldn't find anyone explaining how it works. So I took this opportunity to do with you some intuitive analysis, meaning trying to understand what each component does in this circuit with no math, or very little math. Using a circuit simulator, I'm using LT-Spice, I'll try to guide you through the same reasoning I did, hoping this can help you building a better intuition in understanding analog circuits. Before starting right away, we need to understand how a curve tracer works. The idea is quite simple. We just need to sweep the collector voltage with either a triangular or sine wave and measure the collector current. These will be respectively the x-axis and the y-axis. In this way, though, we obtain only one branch of the characteristic. If we want more branches, as I've shown you on the oscilloscope, we need to vary the base current as well. The best approach is to use a sort of stepped ramp, like this one. This way, we have multiple base current values which are constant during the sweep of the collector voltage. Now that this is cleared, we can delve into the analysis. We'll analyze each part separately starting from this circuit here. You might already know it, this is simply a bipolar astable multivibrator, and it gives out a sort of square wave. Why sort of? Well, if you look at the voltage here, you can see that who designed this circuit chose R1 and R2 values so that the rising edge is very slow. But I'm quite sure this is intended, and you'll understand why in a moment. Let's start analyzing this branch here. We can disconnect the rest of the circuit. This is simply a low-pass filter, and if you look at the voltage of this node, you can see how with this low rising edge of the multivibrator, it gives out a kind of triangular wave, which is exactly what we need to apply to the collector of our transistor under test. If we used a better square wave, like this one from this ideal generator, you wouldn't get the same effect. Now, how do we apply this voltage to the transistor under test? Well, through Q7. Q7 forms a common collector stage, which basically acts as a voltage buffer. The voltage on the meter will be equal to the voltage on the base minus the voltage drop of the PN junction, and moreover, it has a very high input impedance, equal to the resistor on the meter times the beta of the transistor. In this way, we'll avoid loading C3 and modifying the triangular wave. From now on, we'll keep the square wave generator as the input signal, just to make things easier to understand, but everything still applies to the original astable multivibrator. It is now time to analyze C4 and D1. Let's give a look at the voltage at this node here. You can see that when the input square wave is equal to VDD, the node voltage is almost equal to 0, while when the input square wave goes to 0, the node goes to minus VDD. This can be explained easily considering charge conservation on the capacitor. The charge Q must be equal before the edge and after the edge. Since Q is equal to the capacitance times the voltage across the capacitor, by imposing Q being equal before and after the edge, we can easily find the voltage of this node, which is equal to minus VDD. We can now connect the emitter of Q3. Note that since the base emitter junction of a transistor is simply a PN junction, this is completely equivalent to doing this. Let's give a look again at the voltage. You can now see a different behavior, which can be explained as follows. Let's look at the input square voltage and the current of C4. Since the current of a capacitor is equal to the capacitance times the voltage variation over time, it is trivial to see how the rising edge of the square wave gives a constant current through the capacitor. In the positive edge, this will give rise to a current flowing through D1, which gives rise to a constant voltage drop. At the end of the rising edge, no more current flows through the capacitor. No current flow means that the voltage drop of the diode should go back to 0 volts. However, you should know that capacitors aren't very happy with sudden voltage variations. Thus, a small current will still flow, giving rise to this transient you see here. The same applies to the negative edge, where instead of D1, the same things happen to the base emitter junction of Q3. Let's now look at the current of the base of Q3. You can see that there is a current flow. Indeed, when this node here reaches a sufficiently negative voltage equal to the PN junction drop, since the base is tied to ground, a positive potential is applied to the base emitter junction, and current will flow through it for a small time. This makes the transistor turn on. In fact, if we connect back the collector and we look at the voltage here, we can see something very interesting. This is exactly the stepped ramp we were searching for. The capacitor C5 is initially charged to VDD, and when the transistor turns on, there is a very quick discharge, but since the transistor is on for a very small time, the capacitor doesn't fully discharge, and we obtain this stepped discharge behavior. Very cool, but this works only one time. We need a way to charge back up the capacitor, and this is exactly the role of Q5 and Q6. If you know something about power electronics, you should know this configuration forms an SCR, or silicon control rectifier. When a pulse is applied to the gate contact, the SCR will start to conduct till the current through it goes back to zero, after which it automatically turns off. You can see here that the gate contact is tied to ground through R7. If you look at the node voltage here, it is visible how after reaching 0 volts, this node tries to go lower than 0. But as soon as it reaches a negative voltage equal to the PN junction voltage drop, the base emitter junction of Q6 is forward biased. A current will flow, which will cause a voltage drop on R7, giving the gate pulse that we need to activate the SCR. The SCR will charge back up C5, and once it reaches again VDD, no more current will flow, and the SCR will turn off. And that's it. We can use this voltage to bias the transistor under test through R6, which should be high enough to avoid discharging C5, and we are done. Interestingly, if we change C5, we can modify the number of base current values by modifying the discharge time. We are now done with the analysis. Now, if you're gonna build this circuit, just one important recommendation. You need to take a floating measure with the oscilloscope. Otherwise, if the ground of your circuit is connected to earth, when you put the ground of your oscilloscope at the collector of the transistor under test, you'll short it out. Usually, power supplies give you the possibility to disconnect the ground and earth. Mine, for example, has this little metal sheet which I can unscrew. If yours doesn't, the best way is to power up the circuit using a battery. Thanks for making it to the end of this very long video. Next week I'd like to show you a couple improvements that I'm trying to implement in this circuit. Have a good one!